Do your thing. Let's give Nick a warm welcome.
All right, so like Johnny said, I'm going to be talking about testing in Go. I'm Nick Gauthier, and I'm nGauthier on Twitter. And I just wanted to give you a little bit of background. Like Johnny said, I'm a developer at CodeShip. For my career, I've been doing mostly Ruby and Rails, and then before that, I do have a CS degree, so doing C, C++, Java. So for me, Go is sort of like coming back to that more formal programming after being in the crazy world of Ruby for a little while. So despite the fact that I've been doing Go for 6 months, coming back to it reminds me a lot of C, except with all the sharp corners sanded off. So it wasn't that crazy to learn Go, especially because Go is such a simple language, which is one of the things I really like about it. Some of my favorite things in the programming world are tests, web applications, and databases. So I'll be talking about tests today. Probably half of all of my talks are about tests because I really, really like tests. And my coworker, Peter, gave me a great tip today to help me not really worry too much about giving this presentation. And he said, tests are dumb and no one cares. So don't worry how you do. So thanks, Peter. I feel great right now. And there's my website if you want to look. It's a pretty technical blog. I only have a little bit about Go on there. It goes back to a bunch more Ruby. So I wanted to start off with like the most basic example of testing in Go. All you really need to do for tests in Go are you've got your package, whatever package you're working in, you don't change it. You still will use the same package that you're using. In this case, I have a package called basics for the testing basics. You import testing. And then any function that you start with test capitalized is going to get run by Go's testing harness. And it will take one parameter, which is a testing T, and you can use that to call the different testing functions in Go. So what I'm doing here is I'm just making sure that true is equal to true. Instead of doing something in the affirmative and saying true is equal to true or we should crash, here I'm saying, if true isn't true, then there is an error. So you talk about things generally in like the worst case with Go, which I think sort of flows well with the way that you write Go, which is generally calling methods and checking errors and then doing something if something goes wrong. So that's kind of how the tests look too. So in this case, I'm going to have an error and print out a nice little string if true is not equal to true. So like Johnny said, we have a nice small group here. Even if we didn't have a small group, I still love doing very interactive talks and discussions. So at any point, if there's anything that you want to know more about, I'm more than happy to talk about it because sometimes there's some nice little hidden gems to talk about that I sort of looked over, but then somebody else might bring up. So if at any time there's something on here that you want to talk more about or ask about, please feel free. So how are we feeling on the basics? All right, cool. I thought you had a question. I was excited. So let's talk about some of the testing functions that you've got on T. You can call errors. You can fail the test. You can see if it failed. Fatal will make an error message, but also stop the test right where it is. You can also just log debugging stuff. So when you turn the verbosity up, you can see all your log messages. So you can leave them in there for yourself later on if you ever have to debug a test. Parallel also will mark one for parallel execution. If you want to get fancy and watch everything break that you wrote, you can skip over them as well. But the thing is, 99% of the time, the only ones you really care about are error and fatal. And all fatal is an error plus a fail. So error, it's like you're making a big list of everything that's going wrong on this test. So you can have a whole ton of errors, and if they all trigger, you'll get them all at once at the end. And it'll be like, this went wrong, and that went wrong, and that went wrong, etc. But with fatal, it will stop. So that's like if you got an error when you were initializing something, and you can't even do your other checks if you don't have that thing. So you have to pretty much bail out of the test at that point. Often, most of the time, I'll just use fatal too, because that's usually what ends up happening, because the tests will sort of depend on the pieces that you create as you go along. But sometimes it's nice if you have like a big object with a ton of fields to be able to do a lot of error statements and see exactly which ones worked and which didn't while you're trying to work on like some database persistence or something like that. So what happens when you run this, I've put the V flag on so you can see the verbose output. And the error will say expected true but got false. and it will then continue on to the fatal that says can't proceed 2 and 4. And the neat thing is here, if you look back at the previous slides, you can just put as many arguments as you want into error and fatal, and it'll stringify them really nice, just like println, to let you see what you're looking at. It's a really nice interface for just putting a whole bunch of different objects all along in the error string to get a lot of good output. So a really common pattern that you see a lot in Go, and so you see it a lot in tests, is errors. So in this case, what I'm going to do is decode some hex, and I put in some invalid bytes that aren't going to decode into hex. And so when we run this, we get an error, and you do the same thing as you do a normal error check in Go, but then you can just give that error directly to t.error, and it'll just print your error out with a nice little line number where the error came out. And that's just a really, really common pattern, so I wanted to show that. So you can pretty much take your code where you handle errors and do the same sort of thing in your tests, catch that error, and you will get your traces out the bottom really nicely. Couple more little tricks here. You can give it a run with a regex, and the regex can just be a string if you want to run an individual test. That can help when like you're refactoring and you make a little change and it breaks everything, and then you have to go hunt down individual pieces, and you want to just scope yourself and say, I'm only going to look at these tests right now and get these to pass, then I'm going to look at the rest of the world. Otherwise your terminal just flies by when you're trying to work. And then V, that'll give you all the tests being printed out individually as they're run through, so you can see the logs and the errors that go with that test. And it'll also print all the log calls, which is pretty helpful. But usually you just do that when you're developing, or maybe on like your CI server, you might want to see them all. But for the most part, when you run the whole suite, you'll take the V flag off. Cool. So I'm going to go into an example about testing HTTP, but before that, were there any more questions on the basics? Yeah.
So the parameters. So the run error is the register, the expression.
Yeah, so in this case, it was any test that has error in the name, and I had one here called test error.
Oh.
So I put error in the name of it. Yeah. If you wanted to, you could quote it, and then you could add different regex characters if you wanted to get a little fancier. But usually I'll just use like the text of it to rerun it. Yeah.
I guess testing is not part of the standard library, or is it?
It is. Yep, the testing package is in the standard library.
Is there any testing functionality to make it like a bit fancier as like our spec or test unit, where you can basically get like XML output or diffing, for example? Like,
I don't know about XML output or diffing, but there are plenty of assertion libraries out there that give you like expect syntax if you prefer that, expect master syntax, and they'll give you a lot of helpers too. So one of the ones you might often see yourself writing is a similar one that you write when you write a main, which is like a check error function, which runs something, and if that thing returns an error, then log the error and fail in the main function, like exit with non-zero, right? So in a test suite, you might want that as well, like check error. Then you can wrap up these sorts of method calls here and say check error hex.decode. In this case, since it's a 2 argument, you'd have to have like 2 check error or something like that. But yeah, I used a lot of those at the beginning, and I found myself getting more and more away from them because I wrote more and more code that was harder to dig through, and I found it better to just get used to writing normal Go in my tests and normal Go in my Go, you know? So I don't litter my Go code with check error functions except for like a main file. So I didn't want to do the same patterns in testing. I think also sometimes the assertion frameworks can cause you to, because you are molding your tests toward the assert frameworks, they don't let you mold your tests toward the way that you want to organize your tests. So I like making my own organization, and we'll talk about that later versus those.
Question.
Yeah.
So the names that you choose when you're writing, when you create the function definitions, is that a way of you namespacing sort of the types of tests, so that way you can run that particular grouping of tests, like from the console that you showed earlier?
Yeah, if you want to, you can have your own schemes for that. Usually the way that I do it is I'll say test, and then I'll talk about what the object under test is, and then I'll talk about the method that I'm going to be testing, and then maybe I'll talk about the conditions around what I'm going to do to that method. So if I have a person and they have a name, and I want to check when you didn't give them a name, but you try to like print them to a string or something like that, it would be like test person to string without name. You know, that would be a good way, I think, to describe it, sort of top down from the object through its methods and the cases that you're working with. But you do have to put the test at the front because that's how Go picks up on what to run.
Is there, so I assume at some point once you get a big enough test suite, you want to somehow separate them, group them. Like what kind of mechanisms do you have in Go? Perhaps you don't get to that.
No, I wasn't going to talk about file organization and structure, but you just use packages. It's just the same way you use your own code. Yeah, your tests have to be in the package that they're testing. Well, if you want to access private stuff. If you want to access public stuff, you can put them in a different package and import the package that you're testing if you want to do it that way. But the gold standard, what you really should be doing is you put the test right next to the file of things that it's testing. So you have person.go and you have person_test.go, and they're both in the like animals package, right? And that's a folder. So you have each individual, you'll just see file test, file test, file test in that package.
See, but if you're in a sense coupling the implementation to the testing in that way, and therefore having access to the private stuff, as you say,
yep.
Don't run the risk of your test knowing a little bit too much about the internals of your
absolutely. Work. Yeah, I'll talk about that a little later on.
Okay.
Yeah, and then the thing is you can always go outside all of your packages, kind of at the root, and write some test functions that are going to be like integration tests, and then import a couple of your packages and point them at each other and run them. That's not always the best way to do it because you have to set a lot of stuff up and that can be difficult, but you certainly can, and I've done that, so yeah. And you can make whatever folders you want for that stuff. But generally, Go developers will put the test right next to the source, and that's a great way if you're in the standard library and you click on one of those methods, and next thing you know, you're looking at http.go, just throw _test on the HTTP and you can see all the tests for HTTP. And I've learned just as much from reading the standard library tests as I have from reading the standard library docs. You go into HTTP and you're like, whoa, there's an HTTP test package. I had no idea. And you can dive through there. You can learn their conventions, how they organize, and it's a great way to learn. All right, cool. Anything else? Yeah.
I was wondering, do tests run in random order, or are they kind of special?
I don't think that they're run in random order. I think that they're run alphabetically, but I'm not positive. They might be run in random order. I honestly don't know. I know that every package is run in parallel with every other package, which is really fun to find out. And the parallel method that I was talking about before, that's inside a single package to have multiple test methods run at the same time as other test methods in that package. But Go will parallelize your packages. And I believe it does not up your Go max procs, so it doesn't actually run them like across all your cores. It just runs them at the same time on that one Go routine or thread. So yeah, but that usually adds enough craziness. Yeah, cool. All right, anything else? All right, let's talk about HTTP. So to level up our example, I wanted to talk about something that a lot of people do with Go, which is HTTP servers. And this way we'll get something a little bit more difficult that we can test without diving headfirst into some of the more crazy stuff. So what I've got here is I have an app that stores a message, and then I'm going to implement serve HTTP on my app. And that's going to mean that this app is going to function as an HTTP.handler. So Go's HTTP server will be able to accept an app because it can serve HTTP. And all that the app does is it writes the message out. No matter what URL you visit, no matter what params you give it, no matter what verb you're sending along, it's just going to write that message back. So pretty dumb server. So the way that I'm going to test this is I'm going to create an app. Then I'm going to use the HTTP test package's new server. And that's a lot like http.server, except they've done a couple of nice things for you. Like you don't have to specify the port that you want to run it on. They will actually randomize the port for you, and if there's a collision, they will re-randomize the port for you. So you get your own little server that's going to work well in a test scenario, and you don't have to initialize that part. And we'll close it when we're done. And then what I'm going to do is I'm going to get on that server's URL. So in this case, we're really testing from the outside. I'm saying if you were to boot up a server serving my app and somebody like hit it as an HTTP client and actually connected to that socket and made that request, what are you going to get? So this is very different from if I had said app.serveHTTP and then given it a response writer and a request object. Here I'm really going from the outside. I'll check my error and I'll register that error if we got one. And then I'm going to read the whole body. And if I got an error reading the body, I'll log that out. Otherwise, what I'm going to do is convert the body to a string and compare that to hello, which is what I initialized the message with. And if that wasn't hello, I'm going to do my error with expected and got. And you'll notice that like I still made expected hello and got as like 3 separate strings with commas. And I really just try to stick to expected, then the first variable, got, and the second variable. And that way it makes it very obvious for me if I'm changing hello, I can change it in a few places. And I'd probably make hello a variable in this test as well, but started to get near the bottom of the slide, so bailed on that. But it's nice to keep that format. Any questions on this one? Does this make sense? Everyone's good? Okay. Because it gets harder. Oh no!
So we lost the
Projector adapter. Technical difficulties. All 3 of you on the Hangout are going to have to hold on a second. I'm going to like... Oh yeah. That's actually the craziest thing. Is the only other one I've done on Hangouts has got so many views. It's ridiculous. I don't want that many people actually just taking what I say for granted. Cool. So what I want to talk about next are factories and helpers. So this was talking about what we were getting at a little bit before, which is that tests are code too. They're not just a bunch of scripts that run alongside your code. It really helps a lot to treat your tests like real code. And this is something I've been doing a lot in Ruby and sort of brought with me into Go. And you'll see this a ton in the standard library tests too. They use a lot of helper methods. They use a lot of factories. Sometimes they'll even take their packages and expose them publicly, like the HTTP test package is usable by anyone who programs Go. It's not just like the HTTP package's secret box of tools, right? So in this case, I wrote 2 helpers to make this a little bit easier for me. The first thing I did was a factory, and this was my fake app, which is going to run an HTTP test server. And here I'll initialize the app with whatever message I pass to the method, and I'll return an HTTP test version of the server. And then the second one that I wrote is get, and you probably want to name it something a little better than get if you were to actually use this. But get, you give it the testing instance that you're testing with, and you give it the server, and you give it a path. And what it does is it makes a GET request to that server and path, checks for an error, and it reads the body and checks for an error, and then it returns the string version of that body. So this is going to do the whole GET for me and send it back for any path on my server. So once I have these 2, my test gets a lot easier to read because I say, build me a fake app around hello, and fake app should probably match my app's constructor if I had one. I'll defer the close, and then I can just say, if the body equals get, and then I'll give it the testing instance, the server, and the root path, and the body's not hello, then expected hello and got body. So now this is way more readable, and this is the sort of thing I would do as soon as I had a second test around my fake app. I would refactor out the factories and the helper methods. And in this case, my get is doing some error checks for me. I don't just have a lot of little helpers that don't really do anything interesting. I made get do some assertions to make sure when I got something back from get, it was going to work. So I probably should have made those errors fatals so that I could actually stop other than keep trying to do things, because I'd probably get nil pointers and stuff, which wouldn't be fun. Cool. Okay. Before we go to the next one, any questions on the factories and helpers? Yeah.
That's very specific to HTTP. Have you found any like more generic mocking or stubbing libraries? Like if I needed to get MySQL or something in the middle, but I don't want to actually set up the whole MySQL server?
Yeah.
I don't know if it actually works in Go. It's like
You can't. You can't like stub, 'cause that's a little too dynamic.
okay.
But mock objects and fakes are really important, and that's like the whole second half of my presentation.
Oh, okay.
So it'll be perfect. Yeah, but it's really big and it's really important. So the helpers help get for me, getting things set up in Go can sometimes start to get a little bit painful as I have a lot of pieces. So that's where the factories help a lot. And then some of the checks become very repetitive, and that's because Go is a pretty simple language. So that's where the helpers come into play. But yeah, we'll get into some pretty cool mock stuff soon. Anything else? Cool. Okay. So that was all about testing individual components, and I wanted to have an example of testing the interactions between components, because that's usually where all the interesting testing stuff comes from, is when you have to have two bigger, more complicated pieces work with each other, and that's when everything becomes difficult. So in this case, I thought of a simple example here. We're going to have a train, and the train can just go or stop. And then we're going to have an engine, which you can accelerate and you can decelerate, and you can also ask what speed it's running at. So if you wanted to make your train go, you'd accelerate the engine a couple times till you were at the speed that you wanted. If you want to slow down, you could decelerate a little, and then if you wanted to stop, you decelerate till you're at 0, and that's your train. So we're going to be working with this for the next couple of examples. So we'll talk about the engine first. Engine's just going to store a private speed. It's also got the getter for speed in the top right. It'll have a constructor that's going to return a pointer to an engine struct. And then accelerate is going to increment speed by 10. Decelerate is going to decrement speed by 10. And that's pretty much it. To test the engine, this is pretty easy. Make a new engine. I'm expecting the speed to be 0. So I have this expect speed helper. We'll see it in a second. I give it the testing instance. I give it the engine. I expect my speed 0. I'll accelerate it, expect my speed to be 10. Decelerate it, should be back to 0. So this is sort of saying engines should accelerate and decelerate in 10 int increments. And expect speed is really just going to grab the actual off of the speed, compare the actual to the one that you gave it, and then give a fatal if the speed was not equal to the one that was expected. So this is another example of having a helper, just so that you don't have to repeat these 4 lines like every single time. Putting this on the slides really made me write a lot of helpers because I ran out of space. So I had to write nice, clear helpers so that I could put it up there. And so it ends up looking nicer too.
Is this a do as I show you, not as I really do type of thing? Or?
No, I do certainly write a lot of these. Yeah. And if you look at a lot of the popular testing frameworks out there, the one I'm thinking of right now is Testify. Testify has 2 modes you can use it. One mode is you can call their methods and you can give the testing object and then the parameters for it. And the other one is you can run their constructor, give it the testing object, and then they'll give you back an object that has all the assertions on it, so you don't have to pass T in for every single time. So like doing helpers in this way is a pretty popular way of passing your test instance around so that other of the helpers can actually be test helpers and make assertions and raise the errors and that sort of thing. There's absolutely nothing stopping you from making assert true and have it take a T and then a bool and have an error if there isn't one. It's pretty easy to write those out if you want them.
What's the more idiomatic way, or is it you can either go either way?
The most idiomatic way is to like write Go the same way that you see a lot of Go code, which is lots of checks and then conditions if things don't work out and returns. But in this case, in tests, it's fatals because that'll stop the suite from running. And then continuing onward. So it looks pretty much like regular Go. You sort of just have lots of ifs with returns and ifs with returns and do a thing, check, return, do a thing, check, return. That's the real pure way of doing it. But as your software gets more complicated, you're probably going to want to have some helpers to set things up. But it should also alert you. If you have a lot of helpers, it means your code's hard to use because it requires a lot of setup. So sometimes it's time to break things into packages at that point instead of creating huge helper factory type things. So you always want to check and ask yourself if that's the direction that you want to be going in. Cool. So let's look at the train. So I've got a private engine on the train. My constructor that returns a train is going to call the engine constructor to give ourselves a new engine. Go just accelerates twice, and stop's going to decelerate twice, and speed will return the speed. And we're just going to hope that people don't call go twice or stop twice. Our code is going to be really simple in this case. It's not going to really handle any negative speeds. Maybe we have reverse. Sure, why not? You have to just stop to go into reverse when you're already stopped. That's how our train will work. But we've got something pretty simple here. And the thing that I really care about is on the left side of the screen, how train and engine are going to work together, and then how they're constructed. And then on the right side of the screen, what I care about is that the train is calling methods on the engine. And it's those interactions that we're going to play around with for the next couple of slides. So I wrote another helper, expect train speed, and this one's going to be the same as expect speed, but for trains. We'll clean that up later, but we need it for now. And the train test is going to be pretty simple as well. Construct a train, go, make sure the speed is 20, because we're going to accelerate twice, stop, and make sure the speed is 0. So it looks pretty similar to what we had before. Any questions so far on the train? Cool. Okay, so this is an integration test because the train actually has to have a real engine, and it actually does stuff to the engine, and that's the only way our test is going to pass. So they're integrated together. We're testing acceleration by inspecting speed. So we're looking from the outside and saying, accelerate, now how fast are you going? Okay, that looks good, decelerate, how fast are you going? But we're not looking at how the train and the engine interact with each other. If we really unit tested the train, we would give it a fake engine that it was going to play around with. We would tell the train to go, and then we should see what the train tries to do to the engine to go, and make sure that go interacted with the engine in a specific way. And notice that this test only is testing go. It's not testing go and stop and speed that the integration test was. We would only care about testing go. So just a note, this example is obviously really contrived, and there's probably no reason to ever do what we're about to do if your code was as simple as the train and the engine in this case, unless you were like practicing testing. In that case, go for it. But if engine was like some remote resource that you had to call over a JSON API through your own train, then, and it was hard to set up because maybe it needs a bunch of authentication keys and it has to be running on a port and all this junk, then we would really want to start faking out our engine so we didn't have to deal with it as much when we were working on testing train. Because we don't really care how the engine works or what it does. We just want to make sure the train does the right things with our engine. So the very first thing that we have to do to be able to work with a fake engine is we have to refactor our engine behind an interface. So to do that, I also tossed in that speeder interface, and a speeder is anything that you can check the speed of. That's going to just help us with our test helpers. It'll also describe engine and train in a way that they're familiar, but not that important to our refactor. Now the big change is that engine, instead of being a struct, capital E engine is now an interface type. It's a speeder, and it will provide acceleration and deceleration. Now what happens is our actual engine is going to become a private struct engine with a little e. So people outside of the engine package will not be able to actually access our engine struct. They're only going to be able to see our interface. Now what our constructor is going to do, and this is pretty fun, is it's actually going to make an instance of the private struct engine, and then it's going to return it as an engine interface. So that's this section down here. So we're going to create a little engine, and then we're going to return it as a big engine, and Go is going to cast it over for us. And it will allow it if our little e engine implements the big E engine interface. And to implement that interface, we have to implement speed to implement speeder, and we have to implement acceleration, Accel and decel. While I was doing this, I thought it was really funny that Accel has 2 C's and decel has 1 C. How dumb is that?
You know what's funny? Little engine, big engine. I have kids. I'm doing story time with kids tonight.
Yeah.
I'm going to talk about little engine, big engine.
Yeah, right. There you go. If you're ever just like, oh, I really don't want to do a story tonight, I'm just going to put Nick's presentation on Go. And it's going to put him right to sleep. It's great. Yeah. So cool. So what we've done here now is everyone who works with an engine is still going to work with an engine. We never really exposed any struct attributes in our public interface. We only used methods. So we're pretty safe, and this refactoring will be pretty easy. So now we can pass the big E engine around. Does this make sense to everybody? Cool. Okay. So to test our real engine, this was the nice little trick I wanted to do. I wanted expect speed to take a speeder and not a train or an engine. So now we can reuse expect speed, which is kind of nice. And that's going to check our speeder. And for a test engine now, it looks the same because we're still calling methods, and our new engine constructor is still going to give us an engine. And this is our external, like, public style test on just engines speed stuff. Although actually I shouldn't say that because we are, oh no, we're calling public speed. Yeah, so this is totally public facing interface stuff for engine. And this test is pretty much the same as when engine was a struct. It's just now with an interface, which means all we can do is access methods on it. So that wasn't really a big deal for engine itself. This is going to change the way that train works a little more. So now what we can do is we can make a fake engine. So the goal of the fake engine is we want to implement the engine interface. So our fake engine, we're going to track the acceleration, the Accel calls, and the decel calls. We have a constructor that's going to return a reference to it. And you'll notice I didn't return an engine interface here. And the reason for that is if I returned an engine interface in my test, I wouldn't get to mess around with the struct fields. So in your tests, usually you deal with the actual fake as a fake type, but then in your code, you'll be dealing with the interfaces. So then I've got Accel, decel, and speed. In these cases, what I'm going to do is whenever you call Accel, I'm just going to increment my call counter, and decel, I'm going to increment my call counter. So this is pretty much the dumbest fake I could make, and there's way more interesting ways to do these. But the goal here was to not actually have to implement an engine, but more to keep track of what the interactions were like. Speed I returned 0 because who cares, we're not playing around with speed today. But usually you would implement everything that was needed to be implemented. Cool.
So you created a fake engine because you're not an engine at this point is not really what's under test. You're testing interaction with it.
Yeah, so what I want to test, the real goal here is I want to test train, and I want to test it without needing to actually use a real engine. And more importantly, I want to test the train's behavior and the way that it collaborates with the engine, not necessarily just how a train works, like a whole train. So the goal of the fake engine is to swap it with the engine, which is what we're going to do next, and then inspect how they interact with each other. Cool. So we do have to do a little refactoring on train, which is the only thing that changes here is this engine here. Since it's an interface, you don't want to pass pointers to interfaces around. It gets very confusing very fast. So you always just pass the interface around, and then you won't actually know if it's a pointer or not, which is a really fun thing about Go. It's hard to figure out if the interface that you're working with is actually a pointer or if it's the actual value struct. But we just want to say our engine is now going to be an instance of the engine interface, not a little e engine. Our train might not even be in the same package as engine, so it might not be able to use the little e one at all. And then our constructor here, we're just going to call the constructor as we normally would. So no big changes there. This is all just really setting ourselves up for the test. So this is the fun part. You'll notice that my test's name has changed. It used to be test train. That was how I tested the whole train. Now we're testing trains go. So to test the trains go, let's actually look at the bottom section here first. We're going to call my constructor that gives us a train and a fake engine. We're going to call the trains go. And then what we're expecting is that the engine had its Accel method called twice. So what I want to say here and what I'm testing with my test is that when you tell a train to go, it needs to accelerate its engine 2 times. Because that's just the API that I picked for my engine. That's how my engine works. But now I'm not checking anymore if its speed was 20 when it was done. You know? So it's really like if you had taken the train and set it up in a warehouse without an engine and plugged something else into the port where the train controls the engine and just made sure it said acceleration twice, as opposed to actually taking a train, putting it on the tracks, and seeing it run down the tracks and if it hits anything, right?
That's more fun though.
It is a lot more fun. Yeah, and when you tell your kids this story, you can do that one instead.
I bet.
Yeah. So for the train with a fake engine, what we're going to do here is we're going to call our train constructor. Then we're going to get a fake engine from our fake engine constructor. And then I'm going to do what's called setter injection, which is where I take the engine and I set it into train. I inject that dependency into it. So I can do this because I'm in the same package. So because this test is in the train package along with train, it can access private methods. So now we can actually screw around with our objects in ways that our users aren't allowed to do. So we can take our fake engine and pop it into the train without it really noticing, and then be able to do stuff with the train. If you need more power than that, what you usually want to do is for your new train constructor to accept an engine to be passed in, and then if the engine being passed in is nil, call the constructor. That would be the most flexible way. In this case, we're just going to do a little setter injection, swap it out real quick at the beginning before we do our tests. And the nice thing is here, it makes it easier to use train because you don't have to also instantiate an engine. The train just sort of comes with batteries included. Cool. So does this test make sense to everybody? Any questions here on this one? Cool. So stop. All we're going to do is we're swapping go for stop and decel for accel calls. So now we have separate tests for the acceleration and the deceleration. And by using our train with fake engine helper, we can just sort of make this pretty easy. And only the code in the test that's really substantial is dealing with the calls and effects that we have in this case under test. Cool. So I wanted to talk about interfaces in general. It's usually a good idea to put an interface for anything that you're going to be exposing publicly, any types that you're going to work with. The only times that you don't really want to use an interface is when you have like data objects that are often going to be value objects. So if something represents like a request payload, you probably want to share the public struct because people are just going to interact with its fields, not really call methods on it. Maybe call your other packages methods that accept those data objects and manipulate them or return information about them. But usually for the real object-oriented things that you want people to use, you want to use interfaces. And that's for a couple of different reasons. The first one is future flexibility, because if you make a really big package all based on structs and calling with structs and constructors that return structs, and you have to refactor that, it is a huge pain to refactor it over to an interface. But if you do an interface from the start, all you have to do is just keep track of the methods that you're going to have on that interface, and it forces you to keep clean that way too. If you really have to explicitly say, you know what, this is going into the public interface, you have to make that decision consciously. You can't just throw it all out there for somebody to use. The next thing is, with interfaces, you have to expose functionality with methods. You can't let people just access struct fields by making them public. And this is really nice because of the uniform access principle, which says that if you're going to work with, if you're working with some data, if you're trying to get some data or really use any sort of thing, you should use it the same way no matter how that data is stored or implemented. So by forcing yourself to always use methods like getters and setters, that means that down the road, if you want to make it more complicated than just a getter for a struct field, you don't have to refactor all the code that uses what you've written. And in the Go world, stability is really, really important. It's something that a lot of people really strive for, not to be able to say, hey, there's a new minor version of my library and everything's broken. Like, you really can't get away with that, especially when we don't have good dependency managers in the Go world. So you have to really go for stability here. Now, the third one is that it's easy to fake. So because we had an interface, it's very easy to make a fake and swap it in, and the library doesn't even know. That's the best part, is that it doesn't even have to be by the author. Anybody, like if I made my train and my engine, they were interfaces, I don't provide fakes, I don't even test my code, whatever, and I give it to Johnny and he's like, this is awful, I need to write tests. he can make a fake engine and inject it into my train if I had that in my constructor, and be able to fake my objects. It also means that if he writes code that's going to use a train, there's already an interface for train that he can make a fake train for. So he doesn't have to create a wrapper just to create a fake. So it's really nice for fakes in that way. It also means that a user can write their own version of something and use it with your code. So I make this amazing train, it's the best, I make tons of money, it's my job, it's awesome. And then some other guy's like, I bet we could use solar panels. And he can just write an engine that uses solar panels, implement the engine interface, and use it with the train I already built. So that's the nice thing about having interfaces available. If my train took an engine struct, he couldn't give me a different kind of engine even if it implemented the same interface. Yeah.
How do you usually make the trade-off in your experience between API design and testability? Because if you have to make everything, or if it's suggested that you make everything that you want to test, like injectables or constructor or something like that, how do you communicate to people? It's like, oh, by the way, I just did it to test this. You're not actually supposed to put your own stuff in there because I might change that interface in the future and then your stuff will break me up.
Yeah, it's a great question. I would say you should always favor the public API. If you're doing your tests, you're going to be in the same package and you can always skirt your own constructors. No problem with that. If you really have to do something redundantly, you can suck it up and you can have something redundant in your code and manage it, but I would favor the public interface. You can also have a couple different layers of constructors. So you can have new train, takes no arguments, and then you could add new train with custom engine, right? And maybe nobody would ever call it, but it's not the main entry point, and most people wouldn't go for that when new train's easier to use. So if you have to sort of have both, you can have more complicated stuff that's obviously more complicated, right? But usually I will just skirt my own constructors and initialize my own struct, and then pass it along as an interface to somebody else. If I really have to get around it and do some crazy stuff for a test, I'll try to keep that under wraps and not pollute the public API with things that I needed. But yeah, you can, for a static language, you can get away with a surprising amount in Go if you've got a couple of interfaces, and especially if you're in the same package, you can go crazy. Any other questions? Cool. All right, I told you it was going to get harder. We're going to test some concurrent code. So with concurrent code, the things that we have to deal with here when we're using our tests, the first thing is we have to be testing coordination. So we're going to have at least two pieces of code moving at the same time, because that's what the definition of concurrent is. We've got at least two Go routines here that are going to be working. So we have to test how they coordinate with each other. The other thing we're going to see a lot are race conditions, and you'll see these both in your code and in your tests, because just the same way as if you use Go's race detector, so if you use Go's race detector, it will tell you when you have data races in your code, which is amazing. If you don't, then you have data races in your code. So you want to use the race detector, and you'll end up with race conditions both in your code and in your tests. And so that's really fun, especially when it's in both at the same time and you don't know what's going on. And then the third thing is waiting for code to finish. The first time I had a web server that I had written with a bunch of tests around it, I was using the HTTP test server, and I had forgotten to close the server when I was done. And the HTTP test server will grab a random port. So whatever, you can create a whole lot of them. Then one of my tests crashed, and it printed the backtrace for every running Go routine, and I had 50 of them because I had one for my tests, one for the test that was running, and 48 HTTP test servers that were just clogging the whole thing up. So you'll get a lot of situations like that where you actually have to wait, just like in real Go code, you have to wait for everything to actually finish before you can say, now my test is done. You really want to bring everything back together before you exit your test. Otherwise, you're just going to throw Go routines all over the place, and it's going to be really hard to debug. So we're going to add something to our engine. We're going to add run, and we're going to add stop. And the idea here is it's like turning the key. We'll turn it on. It'll be running, and it's sort of running off to the side. And then we can send our acceleration, deceleration instructions to it. And then when we're done, we have to stop it and turn it off. So the engine's going to run in its own routine. Or the better way to do it, which is the way that we will do it, is that run runs in the foreground, and it's up to you, the train, to background your engine. So that's how we'll set it up. So what we're going to do here is we're going to create a new version of Accel, and it's going to be a blocking version of acceleration. So the idea is that you push the acceleration button, and then the train maybe slowly ticks up until it's gone up 10 integer units. Then Accel will return and say, we have successfully accelerated 10 points. So to do that, we're going to use a channel. So my engine now is going to have a stop channel where you can tell it to stop. It'll have a done channel to say that it has successfully stopped. It's going to have an acceleration command channel, which is where you will send it acceleration commands. So you could push the button like 8 times really quick, and then it would wait all the way until it got all the way up to 80, right? Then if you look, you can glance at the bottom real quick. The Accel command, all this really is it's got a done channel. That'll let us know when that acceleration command is finished. So again, you hit the button a whole bunch of times, you want to know when each one is done. And then we've got new Accel command, which is just going to be a nice constructor, because I don't know about you, but I always forget to run make around my channels, and then they're nil channels, and then they block forever, and then I don't know what's going wrong. So I really like to make constructors whenever I'm working with channels, or I'll forget to initialize them and not know what's going on. So then the way that Accel is going to work on an engine is the first thing you do is you instantiate an acceleration command. Then what you'll do is you'll send that acceleration command down your acceleration command channel and say, hey, somebody from the outside, they've told me to accelerate. All right, go ahead. I'm going to throw this down to the engine room, and they're going to handle the acceleration. And then what you do is you wait on the command's done channel. So that comes back and they say, okay, we've accelerated, and now I can go back to my caller and return, since the way my interface is going to work is by blocking. So I send the Accel command off. Right now we're not handling it all. That code's not on this slide, so don't freak out if that doesn't make sense, because it doesn't. And we'll wait for it to be done when it comes back. So to go along with the blocking Accel, we have to have an engine run loop. So what this looks like is our engine's run is going to be in a for, so it's going forever, and it's going to be selecting on 2 channels. The first one is the Accel command channel, and the second one is the stop channel. So if we get a stop, what we're going to do is close our done channel to say, I've received the stop, I'm now done, and I'm going to return out of my run loop, so I'm good. If we get an acceleration command, now we're going to increment our speed, and I also threw in a sleep just for fun to make things hard. And then I'll close my commands done to say we've successfully accelerated, and I'll go back into my loop. So what this means is if you were to hit that button 8 times really fast, you'd get a bunch of people waiting to send on your Accel command channel. One of them is going to get through and be in the Accel command channel. This run loop will come off of its select, pull that acceleration command out, increment the speed, sleep for a little bit, say this command is done, throw it away, go back into the loop, grab the next acceleration command, accelerate it by 10, sleep, close that one off, which will make that one's Accel return, which means that everybody's Accel method from back here is going to return when their Accel command finished. So those are all nice and coordinated. Cool. So what this means is that if we want to accelerate, we have to have running at the same time. If we try and call Accel and we're not running our engine somewhere, it's going to get into a deadlock immediately, because it'll be trying to send on the Accel channel and nobody's listening. You also notice I've omitted the decel here. I figure you're all really smart people. You can figure out how to flip this around and subtract 10 instead of add it and do all the decel stuff. So we're just going to talk about Accel because I only have so much slide room and I like big fonts. Cool. So questions on this? Make sense? Cool. Okay. So here's stop. All that stop does is it sends a true down the stop channel and waits for done. Because what could be happening is when you call stop, you could be in the middle of an acceleration. And what we want to have happen is that acceleration needs to finish, then it needs to go back into the select, and then it will grab the stop and receive that. And this is really nice to make sure that you don't end up getting cut off in the middle of doing anything, but instead you will stop after you've resolved all of your outstanding work. And actually, not necessarily all of your outstanding work. We could stop while there's a bunch of messages on the Accel channel. So it'll be important for us to close out the Accel channel here as well, or to have people sending be listening on done. But I didn't really cross all my T's and dot all my I's when I was writing this. Just enough for us to play with some tests. Cool. So this is what concurrent tests look like for me. At the beginning, I'll do my setup. In this case, I'm going to instantiate my engine. Then I'm going to have my own done channel, because what I'm going to do is I'm actually going to background my Accel, but have my my foreground code be doing the testing. And really, it's totally up to you which one you want to do in which scenario. You can background your assertions, or you can background your code. I usually like to background my code because I want my test code to have the most control over the execution environment in this case. So what I'm going to do is I'm going to background my acceleration, and then when Accel returns, I'm going to close my done. And this is important, like I was saying before, about cleaning up all your Go routines. So this done close here will allow us to receive off of done at the bottom. So that means that this test function can't finish until this Go routine has finished. That'll make sure that everything's cleaned up when it's done, and Accel didn't just block forever and my test went on and I wasn't able to really do anything. So then what I'm going to do is this guy gets backgrounded. It's going to go and send an acceleration command. And what my test is going to do is make sure that I received an acceleration command. And I'm using the, oops, I clicked. I'm using the 2 format version of receive. So I'm going to get the acceleration command, and I'm going to get an OK that's going to tell me the channel is open, not just that it closed. So I'm going to make sure that if the command is nil, that's an error, because I expected a command. And if it's not OK, meaning the channel's closed, that's also an error. So in this case, I'm unit testing Accel, because I'm not even testing the train zone acceleration with the train zone run loop here. I'm just making sure my accelerator sends the right command. Now, if this was a more complicated command, like something that's going off to an API or forming a complicated structure, you would want a unit test like this, so you could make sure that the message being sent by Accel was appropriate. But like we talked about a little bit earlier, here we're really testing under the covers. We're unit testing only private implementation information here, and that comes with its own trade-offs. So this code is going to be this test will be very brittle along with the code that it's testing. If you wanted to change any of the private implementations, you have to change the test to go with it. So these sorts of tests are often very useful for development, but maybe less useful for regression and not useful at all for refactoring. So keep those trade-offs in mind when you do tests like this under the covers. The main reason that this is my example for you is because I wanted to stay inside the train and engine world, and I wanted to show a simple example of concurrent testing without taking up a ton of slides that you'd have to hold together in your head as I flipped back and forth through them, because Go code can get pretty wacky once you get into concurrent stuff. Yep. Okay. So then the next one you can look at, this is our integration test, which we can still keep around for the engine. And here, this is where I'm testing the whole engine. This is the kind of test that you really want to keep around, because it'll work off of the public interface and about how it expects the object to interact without concerning itself with the private implementation. So this one, this is testing concurrent code, but you barely even know it, because you're going to call run and stop will wait for the engine to stop running, because that's how we've set up our API. So we have a really nice concurrent train here, because you don't have to do any done channel closing, monitoring, and go func type stuff. You can just say go run and defer the stop, and then do a bunch of assertions. So this is the kind of test that I really like, and I really like to keep around, because it's super easy to read. It tests a whole bunch of code, and it's not going to change if we add solar panels to our train. We can do all kinds of stuff. Cool. Any questions about the concurrent test or our integration test? Pizza's kicking in. All right, so a tip. This saved me a ton when I figured out how to use it. I was using GDB for a little while to get back traces, but it can be, it takes a moment to set up GDB, bind it to a running process, to get a backtrace, to inspect that. But what's way easier is control /, which is a sig quit. You'll see I was running my engine test. That's the normal test output. Then there was this control / sig quit. And then you can see my Go routines. And what it will do is print out all of your Go routines and exactly where they all were. So it's saying, all right, Go routine number 6 was in test engine, and we were on our train test Go line 89, and this guy was running. This one was receiving on a channel, and that was actually the test suite itself, so I clipped that out of the output here. And then the 5th one was another channel receive, and that was train test 63. So that was most likely the Accel inside the function and the receive outside. And I probably went and like turned off the command send. So it would get kind of stuck there, because you will get deadlocks when things deadlock, but sometimes you don't get deadlocks when things deadlock. And it usually happens when a couple of things all depend on each other, or something is in like a timing loop and it's just checking and sleeping, which is really not how you want to do things, but sometimes you have to. And you'll get deadlocks that don't actually deadlock. And then control / is very, very, very useful. So at this point, I wanted to just have a little brainstorm, see what people thought about this. So how would we combine the fake engine idea with the concurrent code idea? So how do you make a fake that can deal with concurrency? So ideas, go. You're on the spot now. All right, first example, make Nick write it.
That sounds hard. Can we go back to the
Yeah. So like this one?
Time that the engine received its events?
Recording time? Yeah, we could mark some timestamps. Or to go a little further, we could have like a log of like events that we had. Yeah, absolutely. What kind of concurrency tools do we have in Go?
Channels.
Go routines, channels, and sync. Yeah, we could use wait groups. Yep, we could use locks. And absolutely we can use channels. Yeah. So I thought accelerator could wait on a lock, like the Accel of my fake could like wait on a lock, and then my doAccel private method could unlock that lock. So that way my engine could block on Accel until exactly my test decided I'm going to unlock Accel and let my code proceed. The other one was a channel. So Accel could wait on perform the acceleration channel, and then my doAccel could send a message saying, go ahead and perform the acceleration. So yeah, and the answer here is that there really isn't a trick. It's the same code, the same libraries you have with Go are available in tests. So if there's anything I'm going to really hammer home, it's that tests are also code. And you can use all your tricks, all your design patterns, all of your strategies in your tests the same way you can in your code. So we can create fakes that use channels instead of actually using implementation for their fakes. We can use slices, like we're suggested, to keep track of all the calls that we have. Then in our test, we could go back through and inspect every single one, make sure they came out in the right order. We could attach, that could be a slice of objects that have the parameters the method was called with. Then you can actually inspect exactly what params were called on those methods. And if you put a timestamp, like you were saying, you could have methods, you could have your code calling like 6 different methods. And you could use the timestamps to totally serialize them back together and make sure that that log was right. So it's all the same Go stuff as you're used to. All the same tricks apply. If you want to dig a little further, there's a neat blog post on the CodeShip blog about creating fakes in Go with channels. This was a pattern that I used that would when you call the method, it takes the parameters you called it with and sends it on like a I just got called channel. Your test can receive off that channel, say, hey, look, a method call. I'm going to send a response back on the channel with the return value, and then have that method return. And in that way, you can have your test actually coordinating every single method call of all of your fakes in exactly the order that it wants it to. So if you have race conditions, one of the great ways to organize that and to even test how that race could come out in a bunch of different ways is by using a bunch of different channels where you can selectively unblock exactly the ones that you want to see in the order you want to see it. So if somebody pushes acceleration and deceleration like crazy in some sort of random way on our train, we could then say, all right, let 2 accels go, then a decel, then an accel, and then 4 decels go, and say, let's see what that looks like, because in the middle of that sequence, we got a negative, it's some crazy bug that you found in production. If you can control all of your channels that way, you can reproduce anything. The other nice thing with this technique is just that if you let yourself just receive the parameters a method was called with and send back a return value, that fake can be used for any piece of code that uses that interface. It's completely generalized. It doesn't have to just keep track of Accel calls and decel calls like could be used in one situation. You could use that fake anywhere. Cool. So I'm going to wrap up with just all of the general tips that I wanted to impart upon you today. The first one was testing from the outside. We saw how the tests from the outside were a lot easier to read. They tested more code, and they were going to be more resilient under refactoring because they weren't coupled to the implementation. Test from the inside if you have to, because sometimes you have to. Sometimes you need that. Sometimes your private methods are actually really complicated, and tests should still help you there. Even if they're a brittle binding to the implementation, it can still be helpful. Isolating with fakes and interfaces. This is good design anyways. So it's not just for having good tests to have interfaces. It's a good design for your code to have interfaces so other people can use it in more interesting ways than you imagined. It's just a side effect that makes it easy to test because it makes it easy to use. And anything that's easier to use is easier to test. Tests are code too. So always use good programming practices. Refactor your tests so that your tests look good and they're easy to work with, because that's where you're going to spend a lot of your time if you're testing. And then I also really like it when package maintainers provide test helpers in a public way. They provide public fakes. They provide public helper methods, just like the HTTP test package. It can be great if, when you're collaborating on a large project and you've created some amazing API, you can hand it to somebody else and say, oh, and there's a fake for it, so you don't have to actually instantiate my crazy API and all of its database dependencies and authentication mechanisms. Here's a fake. That's always a really nice little gift when you're writing a library. Plus, it helps you write your own tests. So. Cool. All right, thank you. Go ahead.
So when I started just using the Go testing library, testing language. And I found, I think a few weeks ago, someone here talked about Go convey. And I started using it, and I liked it because it had code coverage. So it's easy to see how much code is tested and
yep.
Does the standard package have anything like that?
Absolutely. Yep. The code coverage is in the standard library. And actually, code coverage would be very difficult to do if Go itself didn't monitor the coverage. It's very hard to do as a third party, maybe even impossible, but I'm not about to say that. But yeah, that's all built in. I love using code coverage. I think it's really important. It's a great way to inspect how you're doing on your code. So yeah, and I think
it's built in and so you can make it part of the test.
Yeah, it's actually one of the flags on when you're running Go test. You can tell it to make a coverage report. The thing is that the Go standard library one will only do one package at a time. And so there's a smaller third-party tool, and I forget the name of it, but it will merge the coverage files and give you, for your whole application, if it's multi-package, what your coverage looks like. And then Go Convey is a bigger test suite and runner and gives you more nicer output. I don't use it, but it looks really nice. So yeah.
Yeah, that's what
But yeah, I love doing code coverage. I think it's great.
There's also somebody else who mentioned sort of the RSpec style testing suite. I think there's one called Gokimba.
Don't know.
Gokimba, something like that. That allows you to, if you've ever written sort of BDD style tests, like expect this to be able to whatever that style of testing. There is a Go package called Gokimba something that sort of allows you to write that BDD style testing. But I don't know, for most Go developers I know, honestly, they just use the stuff that comes with Go.
It's true. It's like the first thing I did when I was learning Go. Like I needed to know also how to test it, and I went right to the frameworks, all the syntactical sugar, and you end up learning how to use a test package, not how to like write tests. And so I think it was more fun to sort of really slog through and learn the hard way. And we ended up removing those frameworks out later as a refactoring for a couple of different reasons. Yeah, I would recommend people absolutely to start with the standard library code. Try and stay there as long as you can. You'll learn more about Go even if it's harder and you're not leveraging other people's code. Once you really know what you can do with Go as a language in the standard library, then look at other people's packages and you'll have a good way to really gauge how much they're doing for you. So one of the classic examples of that is like the Martini web framework. Was written pretty early on when people were like right at the sharp rise of Go. It was written to be a really easy to use web framework, but it was written by a person who didn't really understand idiomatic Go. And I'm not being rude. He said that, and then he wrote a new version called Negroni, which was more idiomatic version. And he really said, I made this really awesome and cute and easy to work with, but then I realized it was hard to work with because it was so easy to use. Because it was not customizable, it wasn't extensible in any way. So it's really hard not to be drawn to really nice, easy to use code like that. I absolutely was, and then went back and refactored a lot of it out. So I would say try and start with nothing. Do it the hard way, build yourself up, and then look at a package and say, do I really need this? Is this how I want to change my usage from being my code here to being what they've decided to expose to me? And you'll notice the standard library often provides lots of different kinds of objects, lots of good interfaces, and they're meant to be composed by you, put together by you. And the good packages out there are the same way. There are lots of components that have clear ways of being composed and used. And the ones that you want to stay away from are the ones that have the tiniest little API that are amazingly easy to get started with, because they will go from 0 to 60 in a day, and then they won't go any faster for the rest of their life. So those are the ones you usually want to steer a little clear from, and dive into the source. I looked into Negroni's source, and it's actually very short. It's very composable. It's really nice. And I realized I didn't even need it because it was so little. I just wrote the parts that I kind of liked and used them. It's MIT license. You can do that. It's great. Yeah. Cool. Any other questions?
So is CodeShape hiring?
Of course we're hiring. Yeah. We have a bounty too, right?
Yeah. Bounty.
Yeah.
Bounty.
Yeah. If you
So,
what's the name of the
who gets the bounty? Is it the guy who accepts the job or
the referrer?
The referral.
Yeah. You don't even have to work for CodeShip to make money.
Listen to that,
Yeah.
guys. You can make money.
Yeah.
Doing work.
You just have to send us somebody.
Just check out drafted.us and
Drafted. Yeah.
drafted.
Yep. Yeah. This is the Web 3.0 of recruiting.
Yeah.
Yeah. Unfortunately, it's not eligible to employees.
Oh yeah, you can't. You
Yeah.
can't claim a
So we
bounty.
need. If anybody out there wants to split it, just let me know.
We'll work out something.
Yeah.
So, guys, don't forget there's some swag right there. If you don't take it with you, don't let it go back over there with it.
Yeah, there's a bunch of cool T-shirts and stickers and stuff. Check it out.
Grab something on the way out. So typically, what we do after the meetup
is we go to Meet Hall. Is it Meet Hall that's supposed to shoot there? For folks who sort of want to hang out for a little bit and grab a beer and whatnot. So if there are folks who want to do that, I'll join you. Please stay for a beer. Yeah, other than that, please, there's a Slack channel. Just pop in there and say hi. There's also Boston Golang, it's up there. If you want to follow us for updates and when we have the next meetup. Our meetups are usually in the last Tuesday of the month, right? But we also have this sort of workshop thing we're trying to do as well. In between meetups, whereby we have workshops on the topic. Right? So the next workshop is going to be on testing, right? So that way you get a chance to sort of apply some of the things that we talked about today in that workshop. The last one we did was around we did a current chat server because we talked about currency in the previous meetup. So it's like a nice way to sort of bake in the knowledge and apply some of the things that get talked about. That way it doesn't go in here and it comes out here. I don't have dates for you on that yet, but definitely watch out for Twitter. Also Golang. That happen.
I wonder if that's why the top is low. Because I think we had maybe the same or slightly more people.
So you're saying they got tired of looking at each other, or didn't want to see
No, I said like maybe because we have 2 meetups in a month. That's why.
Right. So yeah. So part of what we're doing as well is basically saying, hey, we don't have to have it back to back like that, right? So a lot of times, one meetup, I know for myself, 1 or 2 meetups a month. That's all I can sort of like life. So for a lot of folks, kind of come out and go around every week is not sort of conducive to their lifestyle. So we're going to try to sort of space it out a little bit to hopefully you guys can sort of think about these things. But yeah, if you have feedback like that, since this is your meetup too, just let us know. We'll adjust it. We want to make sure it's of value to you guys. Cool. Yeah, other than that, thanks for coming out, guys. This was fun. And I have grab a box of pizza on the way out or something.
Yeah.
Definitely welcome to do that. Thanks again for hosting us, and thanks Nick for coming out and doing this rezo, man.
I will. I'll share the slides, and also all the code that was in the slides is actually part of a repository that you can run. That's linked there, so you can download that and you can run Go test and you can tweak some things if you want to play around with it. And that's my Twitter on the right, and my public policy is that I'll answer any questions if you post them on a public forum, like something like Stack Overflow, where you post it just on Twitter, you post an issue on GitHub. If it's in a public place, I will come and give it a shot. So
no private consulting via email or something?
well, I charge for it. Yeah, I mean that's the road you want to go down. I mean, public is free, so take that.
Awesome. All right. And we